invitation. It's really my pleasure to speak here and to join you. So, an efficient graph-generative model for navigating ultra-large combinatorial synthesis libraries. So I'm at Atomwise, as you already mentioned in your introduction. Atomwise is a preclinical AI-enabled biotech company. We develop and apply AI for drug discovery. So here in the US, we have a saying like, eating your own dog food, and that's what we do. We develop and apply the AI throughout our discovery pipeline, from hit discovery to hit to lead to lead optimization. Today, I'll talk a little bit about what we do at Atomwise. I introduce our structure-based discovery engine. Then I'll talk a little bit about what we do beyond hit discovery. In particular, there's a lot of excitement about generative AI. Talk about the opportunities and challenges that we see in generative AI. And then I'll talk about a method that we have developed in generative AI that returns compounds that are guaranteed synthesizable. All right. At the heart of our hit discovery process is what we call a global structure-based model to predict bioactivity and potency of compounds. And what we mean by a global model is that it is trained on all pharmacological compounds and their targets simultaneously to predict bioactivity. And so we train this model on active compounds and inactive compounds. And that's in contrast to, for example, a ligand-based model, where for each target individually, you train a separate model based on known chemical matter. So you have starting compounds that you start from, and you train a model to predict activity. And we've seen a couple of examples today about the application of such models. Now, the structure-based model has the advantage that it has some sort of network effect. You can imagine that the sort of elements of molecular recognition get transferred from target to target, and so you don't necessarily need a starting chemical matter to start applying a global model for hit discovery. And this is, of course, very important if you go after difficult to drug targets. We heard c-Myc today. KRAS is another example. So you overcome what is called sort of the bootstrap or cold start problem. All right. A little bit about how we train our global model. We generate 800 million high-quality co-complexes computationally for our model. That includes more than 4,000 targets, including 500 validated allosteric sites. AlphaFold came along a few years ago. We currently have 1,300 AI predictive models in our pipeline. For each of the targets, we generate an ensemble of binding sites. So we have about 25,000 flexible binding site confirmations in our model. And we also expose our models to what we call negative poses to help it understand and recognize poor poses that are not bioactive. When all is said and done, we have spent about 172,000 GPU hours and nearly 1 million CPU hours on just generating our training data. And we do this routinely about twice a year. And so this does not include model training itself. All in all, there are about 20 million data points in this, mainly PKI measurements. We take our machine learning models very seriously. Most importantly, we want to make sure that they generalize properly. For that, we have designed a number of benchmarks. We have a diversity benchmark. Do our models generalize across like very distinct targets? We have an allosteric benchmark that tests whether our models generalize to allosteric sites. And we do this both for high throughput screening, so for bioactivity, as well as for potency predictions. And for the latter, we have a compound series we have designed a compound series benchmark that tests specifically, can we rank compounds in the series appropriately with our machine learning models. Now, we also know that machine learning models are eager to cheat on us. So we have designed anti-benchmarks to test for that. Just to give you a few examples of what that looks like, we have a benchmark that we call frequent flyer. So are there compounds that always rise to the surface for different targets? We have what is called a bias panel. Are there certain chemical groups that always rise to the surface in our models? We have a Picasso benchmark that is designed to test whether a model gets confused by nearby features in the binding site, and I had already mentioned the unphysical poses that we test on. So how do we apply all of this in our hit discovery pipeline? So here's kind of an outline of how we think about that. We call it machine-adjudicated drug discovery workflows. We make it a point that we minimize human involvement in the drug discovery process. So this is entirely automated. We start with a target of interest on the left-hand side here. We create a conformational ensemble of the target of interest composed of PDB structures, AlphaFold structures. We have internal software that allows us to create an ensemble from static structures. Then we create co-complexes where the compounds are retrieved from a massive chemical library. Our sort of run-of-the-mill library is currently about a trillion compounds. After the docking, we rank the poses with a deep learning tool we call Pose Ranker, and then we apply both our bioactivity and potency models, as well as some ADME predictions to the model. That gives us a subset of the compounds that we might be interested in, and then we go back to the library and find out, are there nearby compounds in that library that could be even better hits. And so we repeat this cycle usually about 6 times until some stopping criteria are hit. Then we automatically create diversity clusters. We score and select the compounds, all without human intervention, and then these compounds go off in an experimental cascade. Usually we design on the order of 6 plates or so that go off in hit discovery to an experimental cascade. Okay, so what happens beyond hit discovery? Well, beyond hit discovery, of course, we are faced with usually a target compound profile, and you can think of this as a loss function for any AI model, of course. And so we have heard a couple of talks this morning already, or this afternoon, for the folks in Europe about generative AI and how that is changing the game. And they're all focused on multi-parameter optimization and often involve active learning cycles. And it's our experience that these models excel in meeting these endpoints, at least computationally, for the TCP. And so our medicinal chemists get very excited about these molecules. We send them off to our CROs, and then things often come to a screeching halt, where we hear that it's very difficult to make these compounds. We can only make 1% of the compounds that you propose, or we get sticker shock because they require very expensive custom synthesis. We're not alone in making that observation. Just earlier this month, a paper appeared in JACS where the observation was made that generative AI is exploring unknown regions of chemical space to find high-performing molecules or materials that can be readily synthesized and applied. And then in the next sentence, the authors observed that generative AI has mainly achieved only the first few words of this aim. And so the challenge with generative AI is not optimization. The challenge is synthesizability. Simultaneously, we've seen the growth of these on-demand libraries. Just a few years ago, we were talking about tens of millions of compounds in these libraries And now we're talking about quadrillions of compounds in these libraries. So the advantage of those, as we've heard today, is they provide synthetically accessible and cost-effective compounds with reasonable turnaround time. And so we asked ourselves, we typically think of these libraries for hit discovery, but can we, further on in the drug discovery process, lean on these libraries to find promising compounds? And so we went back and looked at all IND-and-beyond molecules and tried to explore if these chemical libraries were sort of complex enough in a way to support drug-like molecules. And so we find that about 70% of IND-and-beyond molecules have very, very close analogs in the library. We use Spacemax, and so 70% of them had an MCS similarity of 0.7 and above. And we're really excited about this, and we're thinking, wow, this would be a great paper. And then this one appeared might look familiar to some of the on the call here, where they did pretty much the same thing and found pretty much the same conclusion, that about 50% of the compounds had an MCS similarity of greater than 0.8. So that's very promising. These libraries contain very complex molecules that are not very far away from an IND quality compound. And so we asked ourselves, can we capitalize on these catalogs beyond discovery? As I said, we would be able to identify compounds with desired properties from these databases with economies of scale from these combinatorial synthesis libraries, that is, low synthesis times and high success rate and low cost. And so the counter argument is, well, maybe the search space is constrained, but with these ever-growing libraries, that may actually not be a problem anymore. And so you could think about turning drug discovery into a massive search problem. The problem, though, is that the current search methods scale poorly with these growing library sizes. And just to give a sense of the scale of this problem, these larger libraries, as I said, they're 10 to the 15, 10 to the 17 at the moment. For comparison, Google indexes only 50 billion web pages. And so this problem is orders of magnitude bigger than searching the web. So to overcome some of these challenges, we started thinking about developing some deep learning tools, and we came up with what we call a combinatorial synthesis library variational autoencoder. It's really generative AI over a synthesizable space. It gives us the best of both worlds, representing large virtual libraries with a generative AI. Okay, so let's think a little bit about the structure of these combinatorial synthesis libraries. Very briefly, we've seen many examples already. Let's take a two-component reaction as shown here. We have the two building blocks on the left-hand side in the Enamine library. They're called synthons, and they form a product by being attached at these attachment points that I've shown here. So the real space consists of optimized reactions with, together with a number of molecular building blocks. And so you can think of CSLs as a collection of reaction tables that look a little bit like this. You have, for a two-component reaction, you have the R groups as columns and rows. The R groups contain synthons, and the synthons form a product. And so any compound in a CSL has a very compact description. It has a reaction ID, and then the IDs of the building blocks that contribute to that reaction. So CSLVAE considers retrieving compounds from a combinatorial synthesis library as an autoencoding problem. And so it has really three components to it. So on the left-hand side here, you see a molecular encoder, then there's a library encoder, and then there's a molecular decoder on the right-hand side. And so let me, without going into too many technical details, let me just walk you through how we designed this tool. We start with the molecular encoder. That's fairly simple. We take the compound, we generate a 2D graph, we run it through an MPNN, and that gives us an encoding that we call a molecular query. Next is the library encoder. So the library encoder creates a hierarchy of representations and keys to represent a library that in turn is used by the molecular decoder. So we start at the bottom of this hierarchy with the synthon encoder. So for every synthon, we create a graph and we run it through a message passing neural network that gives us the encodings for the synthon. And then for each of these encoding, we generate what is called a synthon key generator, just using a simple MOP. So one step up in the hierarchy, we take these synthon encodings and we run them through a deep set neural network to create an R group representation. And that's a collection of vectors. And then finally, at the top of this hierarchy, we take these R group encodings. That's a set of vectors, and again, we run it through a deep set network to create a reaction encoder. And that, in turn, again, is a vector. We run this vector through a reaction key generator, really an identifier for that reaction. And so we have a representation of the hierarchy in terms of synthons, R groups, and reactions. And the molecular decoder sort of reverses that process. So for any molecule inside or outside the library, we can create, of course, a molecular query by first running it through an MOP, and then we create a reaction query for that molecular query using an MOP. And then we compare that to the reaction queries that we have generated for the library, and that generates a probability distribution that you see here on the right-hand side. And so we first decode the reaction. Once we have the reaction decoded, we generate a synthon query, again with an MOP, and we compare the synthon queries for each of the R groups, and again that generates probability distributions. And so for each of these, once the reaction is determined, for each R group, we select a synthon with the highest probability, and that's it. We get a molecule out of the library, whether we started with a molecule within the library or outside the library. So CSLVAE is very efficient. It encodes libraries logarithmically in time and space. And just very briefly, how we train it. This is an example shown on Enamine REAL Space from about a year ago. It had 16 billion compounds in the version that we trained on. We use Enamine REAL here, but it could be used on any library. We train it on sampled subset libraries, 20 reactions at a time, each with 100 products, together with all combinations of their synthons. And so each reaction could possibly decode it in up to 1 million compounds. We run this for about 150,000 iterations. And it's very fast. It can be trained on a trillion-sized compound library in about 3.5 days, at least the latest version that we have so far. Alex asked earlier, so how big is the Enamine library in file size if you completely enumerate it? It's big, and that's the reason we stopped fully enumerating libraries, simply because it's too costly. In contrast, Real Space encoded by CSLVAE is about 170 megabytes. So you can run this on your laptop, and we do. So CSLVAE is guaranteed to remain in library. That's by design, any compound that we ask it to generate will be contained in a library. There are alternative graph-generative approaches that can generate compounds for us. And we compared it to the rate at which those remain in the library if we train it on the same library. So two such examples are JTVAE, the junction tree variational autoencoder, and Rational RL, both out of MIT. We retrained them on the real library. There's a couple of take-homes from this table that I'm showing here. You can see that all produce valid molecules. But JTVAE and Rational RL do a sort of post hoc check on the validity of the molecules and discard the ones that are not chemically valid. CSLVAE by design produces chemically valid molecules, so don't need a check like that. It has far fewer parameters. And you can see that the in-library proportion here is 100% for our method and goes down as low as 3% for JTVAE, even though it was trained on Enamine. Just very quickly, a few slides to give you a sense of what this looks like. We looked at what latent space looks like for CSLVAE. What you really want is that it sort of very smoothly as you traverse chemical space. That means if you make small perturbations to the query, you expect minor edits in the molecular graphs that it returns. And so we tested that by interpolating between source and target compounds, and I'm showing that on the right-hand side here. This is our source compound, and the right lower bottom is the target compound. And as you read this in sort of raster order, you see that the compounds gradually change from the source into the target, and the ordered pairs below the molecules are the ECF-before tandem-outer similarity between source and target. And so it's a nice feature that you can traverse the libraries in latent space. So then we tried analoging with CSLVAE. Bear in mind that it really wasn't designed at this point to analog enumeration, but this seemed like an interesting exercise to go through. We looked at analogs for 24 small molecule drugs approved by the FDA in 2021. We asked it to enumerate the top 100 analogs in the library, and for comparison, we used Author, which is an interesting leading software to perform this operation. Now, bear in mind, CSLVAE is a stochastic procedure, so we repeated that 30 times and took the average. We also compared it to baseline, where we also repeated it 30 times. And in the table here, what I'm showing is we computed the ECF before to the query compound, and then retained the top compound for each of these methods. And what I'm showing here is the quantiles of these top 1 similarities averaged over the 24 compounds that we showed. So the middle row here is Author, which is really the industry standard. And you see that even though CSLVAE was never designed to specifically do this, we don't lag very far behind what Author is doing. In fact, the top compounds look even better than the ones that Author returns. Of note here, though, is that the time it took. This whole procedure takes about 10 seconds on a single node K80 GPU, compared to 30,000 seconds using Author running on 100 nodes, 8 CPUs each. So this is a massive speed up, and we can currently also doing this on a laptop. So finally, just to give you an idea of what these analogs look like, if you start from an in-library compound, you get of course, you get compounds that are in the library back. Interestingly, it finds itself in the library as an analog. If you start from an out-of-library query compound, you get very similar numbers for the Tanimoto distance to the query compound. All right, in summary, the library can be encoded in time and space complexity, logarithmically in the library size. Retrieval also has logarithmic time and space complexity. I didn't go into this, it's a little technical. There's only one step of auto-regression in the decoder. That's really difficult in graph-generative models, that you get this long chains of auto-regression. That's why they don't perform that well. We've overcome that in our implementation. As I said, the molecular encoder can take an arbitrary molecular graph as input, but the molecular decoder guarantees that all retrievals are contained in the library. And it's inductive. The library itself is an input to the decoder, so you can easily swap that out with another library. That's it. Thank you for your attention. Most of the work here has been done by my colleague Aryan Padawi. He actually done most of the work, pretty much all of the work, including the design. And so I want to acknowledge his contributions accordingly. Thank you.